Do you remember that we did something called reflection last time? Reflection. Reflection is, let's say we have a string and let's say we have a hard boundary here. So hard boundary. And if I send a wave or a pulse this way, what will happen is it will reflect back from this side. So depending on this boundary, your reflection can be either like this. So this is with a phase change of 180, right? It is inverted. So if your boundary is a hard boundary, it's going to be inverted. And if your boundary is a soft one or a free one, then your reflected wave will be something like this. It will not be inverted. Okay, so you all know this reflection. Why did I remind you about this? Because standing waves are created due to reflection. And also, you have to know what resonance is. So any object, any material has its natural frequency. There's a natural frequency for any material, any object, anything. Okay. So if the frequency that you provide, for example, if you look at this diagram, a person is oscillating this, right? So a person is giving an external frequency. So if the external frequency that you provide is equal to the natural frequency, so external, if the external frequency that you provide is equal to the natural frequency, resonance happens. That means the object starts resonating with the frequency. It starts oscillating with very high amplitudes. Okay, so you're okay with what resonance is, right? So it's a concept. So if we look at this scenario, if look at this picture, here this is an example where resonance happens. Resonance happens means the frequency that you provide is equal to the natural frequency of this wire. Okay, so that is one point. And also when you provide a frequency, when you provide oscillation, we know there is going to be reflection, right? The wave is going to go this way and come back. So these incoming oscillation and the reflected oscillation will interfere together and create something called a standing wave. So to create a standing wave, you need two things. There is reflection and also there should be resonance. Okay. So when that happens, there will be standing waves. And what are standing waves? So what is the special thing about standing waves and why do people call these standing waves? Why do they use this word standing? So the reason is, so there are different types of standing waves, and in this lesson, in chapter 11, you will be mainly working on strings where the two ends are tight or not free to move. Yeah, like here you can see this end we have like some person is like stretched it from this side and it is also bound from this side. So in this lesson we'll be only looking at things like this. So We call this a standing wave because when this wave pattern occurs, it looks like the wave is not actually traveling. It looks like it's a standing pattern. Like always, these two ends stay immobile. It doesn't move. So these two ends do not move. And the midpoint, it moves, it oscillates, but it oscillates very fastly. Like when we look at it, it really looks like this. It looks like immobile. As it looks like the wave is not traveling, and it looks like a bulb, like onion. Okay. So that's why we call them standing waves. Okay. And another thing is, can you see that, like I said, these two ends are bound. These two ends are bound, right? Those are two fixed ends. So because of that, so this is a must. Always, okay? Always, these two nodes should be nodes. These two sides should be nodes. Nodes means points which do not move. So always they have no amplitude, these two ends. So we have to look at the boundaries. So this is a string bound in both sides. So the two sides cannot really move. So they are nodes. Okay. So that is the condition. So like I'll talk to you about what these things are, what these two pictures are. But even in these two pictures, can you see the two ends? Two ends have nodes. They are not oscillating with the amplitude, right? Those two ends are like tightly bound. They are not oscillating. They are nodes. This is a node. This is a node. This is a node. Okay. So are you all okay with what standing waves are, what resonance is, and why these two ends do not move? Yes? Okay. So resonance, so an object can have multiple natural frequencies. Okay, so there can be resonance at multiple frequencies. So the fundamental frequency or the lowest frequency, okay, the lowest frequency the resonance can happen is called the fundamental frequency or the first harmonic. Okay. So how do we draw this? We draw it like I said before, the rule is the two ends should have nodes. So what kind of a thing, with what is the like simplest form that you can draw it? Both ends nodes like this, right? There's no other way to draw it. So it is the, okay. So can you repeat the definition? Okay, I'm getting so many questions. Resonance is when the external frequency that you provide, okay, the external frequency that you provide is equal to the natural frequency of the object. So here it's a string. When that happens, resonance occurs. Okay. And fundamental frequency is the lowest frequency resonance can occur. Okay, or not. Lowest frequency, a standing wave can occur in this one. Okay, so there you will learn a lot of other examples in chapter 12. So on Wednesday, we will look at more examples on this. And we also call it the first harmonic. And the second harmonic is, what's the next simplest form? So you have to have two nodes at the two sides. And the next simplest form is this, right? You have two of these onions. Okay, so we call it the second. So third one is with three of these. One, 2, 3. So these can keep on going. There can be even 100 of these stuff, and it will be your 100th harmonic. Okay. We will go to derive the equation for this in the next slide. So are you okay with this? And do you get how we draw this? So first harmonic, or the fundamental one, is the simplest form that you can draw it. And at each next harmonic, we add one more node. Sorry, one more this thing. Okay. So why aren't we considering the nodes in the middle? So these are nodes in the middle. These are also nodes. But these two are the constants. Like it is like the limitation. So definitely those two should be nodes. Those two locations should be definitely nodes at any frequency, because they are bound. Everything else, these nodes, the string can decide to do it. So the string will have freedom to change the location. Can you see when this goes to the second harmonic, it has nodes in these two locations. It's not the same position as the second one, right? Okay. So these two nodes are the boundary conditions, like they kind of decide your node pattern. And as you increase the harmonic, you can keep on adding nodes or these bulbs. Okay. So in the middle, there's no limitation, but two ends should be definitely nodes in this tree. Okay. So now we are going to derive the equation for this. So assume that the length of our string is L. Okay. And you all know what a wavelength is, right? So usually a wavelength is something like this, from here to here. So thinking along this definition, can you all tell me how many wavelengths are in this? So there's just one, right? So you can think of like one part, like it's like this, right? You only have this in this diagram. So here you have half a wavelength. Okay, half a wavelength is equal to L. L is the length. So why are we doing this? To get the lambda. So I'm doing this to get the value of lambda in terms of L. That is what I'm trying to do here. So are you okay with this? You see that it's half a lambda is in 1L. Yes, okay. Now look at the second diagram. So this is the second harmonic, right? You'll know what harmonics are. This is the second harmonic. So how many lambdas are here? So there is one full wave here, right? One full wavelength. See, you have this shape here. So that means the lambda here is equal to L. So I have used a different lambda 1, here lambda 2, to show that they are different values. Different because this lambda is bigger, right? sorry, this lambda is bigger than this. So we can keep on doing this. So here we have how many lambdas? We have 3 half lambdas, right? We know one of this is half a lambda, and there are 3 of those. So 3 over 2 lambda is equal to L. Okay. And there are 4 here. That means how many lambdas? We know one of these is half of a lambda. And how many of those? 1, 2, 3, 4. 4 half a lambdas. Okay. So what you can see is when you keep on writing this, you can see a pattern. So here 1 over 2, you can even, this is like 2 over 2, right? 2 half lambdas in this one. And in this one, 3 half lambdas. In this one, 4 half lambdas. So if we keep on doing this, you will see that you can write a general equation like this. N over 2 lambda is equal to L. So when you keep on going from one harmonic to the other, what really happened was this number increased, right? By 1 by 1. See, 1, 2, 3, 4. So if you go to the nth one, or like let's say 100th one, what will change? There will be 100 here. Okay, so we have this equation. So I said I do this, I wrote all of this just to figure out the lambda, right? So if I, since I, so if I use this equation and try to find the value of lambda, what should it be? Lambda is 2L divided by N. Yes, I just made lambda the subject of the equation. And also we know N can be 1, 2, 3, anything, right? It can go from 1, 2, 3, 4 till I don't know, so many values. So I'm going to write a tiny n here to symbolize this is the lambda of the nth harmonic. So here, if I plug 1 for n, I get the lambda of the first harmonic. So when n is 1, lambda will be 2L. So this is the fundamental lambda of the fundamental pattern. For the first harmonic, second harmonic, it will be this, right? 2L divided by 2. You get it, right? Okay. So when you get a diagram, or when they say, so in questions you will see, they will say the string is this much of length and there are 5 of these envelopes, so 5 of these things, and what is the lambda? So you should be able to find the lambda. Okay, so we will do problems. And the other thing is, so we have the lambda. If I ask you to find the frequency, how would you do it? V equals F lambda, remember this equation from last time? So frequency is given by V over lambda. So what is the velocity of a string? What is the velocity of a string? Tension divided by MOL. You remember this equation, right? from last time. So for the string, we just found that the lambda is given by this equation and the velocity is given by this equation. So velocity is this ft divided by m over L, and lambda is in the denominator. So you get 2L divided by n. So this is the equation. So you don't have to memorize any of this, but you should be able to follow these steps. You should be able to write an expression. You have to write an expression to find the lambda. You should be able to do that. Look at the diagram, figure out how L and lambda are related. Okay. So after that, you can use this equation to find the frequency. So in the problem, they will tell you what is your n. So they will tell you find the frequency of the third harmonic. So then you know your n is 3. Or there are 3 onions, or I don't know what you call them, envelopes in the Y. Okay. So we just did this one, right? For a string. So we did the string. In the next lesson, in chapter 12, we will learn about this and this. Okay, we will learn about closed pipes, open pipes, and things like that, which we are not going to do today. Okay, so let's start problems. Like I said before, what is the definition of resonance? Resonance happens when the natural frequency is equal to the external frequency, right? So answer should be B. Its frequency is the same as the frequency of the external source. That is the definition of resonance. Have you seen those bridge videos, like bridges falling down because of resonance? So like let's say there's a bridge. So there's an actual bridge and some external source has the same frequency as the bridge. Then what will happen? The bridge is going to oscillate at its natural frequency at a like huge amplitude, and it's going to break down because the materials are not flexible, right? So they're going to break down. So in real life scenarios, like in constructions and stuff, they try to use materials and do constructions so that its natural frequency is not in the normal frequencies. Like day to day, they try to avoid day-to-day frequencies in those constructions because you don't want a building to fall. Okay, so this second problem is a very common type of problem, and it is very easy. Once you know how to do it, it's going to be very easy. The frequency of propagation of a transverse wave on a 2-meter long string fixed at both ends is 200. Which of the following is not a resonant frequency? So how would we do this? So the easiest way that we can do it is find the fundamental frequency. Fundamental or the first harmonic. And all other natural frequencies will be multiples of this, right? So if I go back, to this equation right here, this one, can you remember that inverse 1, 2, 3 like this, right? So when n is 1, you get the fundamental frequency. When n is 2, you get twice that, right? When n is 3, you get thrice that. So all other harmonics in a string are multiples of the fundamental frequency. Okay, so first harmonic of the fundamental is F naught, second one will be 2F naught, third one will be 3F naught, and the 100th one will be 100F naught. So how would you do it? You will first find the fundamental frequency and then see which one is not a multiple of it. So that is what I'm going to do. So the fundamental frequency is when the wave is like this, right? This is the simplest form. So here you can see lambda over 2 is equal to L, because this is half a lambda, is in length L. So your lambda is 2 times L. So V equals F lambda, and your F naught, when you apply lambda naught value, what you get is F naught. V divided by lambda naught. V they have given as 200, and lambda naught, we know it is 2 times L, right? Which is 4. So when I divide 200 by 4, I get 50. 50 Hertz. So what is not a multiple of 50 here? 50 is a multiple of 50, 100 is a multiple of 50, 200 is a multiple of 50, 25 is not, right? You cannot have half of the fundamental frequency. So A is the answer. So do you get it? So that is a very common type of problem. So next problem, I think we'll have a similar one. Okay. Okay. The next one is all three of these are very similar. So find the fundamental frequency. If they have given, it's fine. If not, find the fundamental frequency and then see whether it's a multiple. So all three problems have the same concept. All the answers you all gave me are correct. So I will first mark the answers and then I will go to the problem. So first one C, second one A, and the third one is again C. Okay, let's see. If a guitar string has a fundamental frequency of 500, that means F naught is 500, right? Which of the following frequencies can set the string into resonant vibration? We know it can be any multiple of this, right? So anything you can divide by 500 will be the answer. 250? No. No, right? 750? No. 1500? Yes, right? It is a multiple of 500. In fact, it is 3F naught. 1750? No. Okay, so it should be an integer multiple of the fundamental frequency. This one, a stretched string is observed to have 4 equal segments. So there are 4 of these. 1, 2, 3, 4. And they are saying this frequency is 480. So what is this frequency? This 4F naught, right? This is the fourth harmonic. 1, 2, 3, 4. 4F naught is 480. Therefore, F naught is what? F naught should be 480 divided by 4, 120. But is that what they're asking? No, right? They're asking what frequency will make a standing wave with 5 of these. 1, 2, 3, 4, 5. So what they're asking is 5 F naught, right? So 5 F naught should be 5 times 120, which is 600. Is it right? So A. So if they asked you to find the fundamental frequency, it would have been 120. So this one, it is also very similar. So I will do it quickly. 3 loops. So we have 3 loops in this. We know 3 loops is 3f0. Okay. 3f0, and they are saying 3f0 is equal to 12. So this is your third harmonic. Okay. So if it is confusing for you, I'll write as f3. f3 is equal to 3f0. Therefore, your f0 is 4 Hertz. They're asking you to find 4 loops. That means they're asking you to find f4. f4 is equal to 4 times f0. We know f0 is 4. Therefore, 4 times 4 is 16. Answer is C. So here, if I was confusing, I will rewrite this. What they have given is the frequency of the fourth harmonic. So they have given us f4. f4 is equal to 4 times the fundamental frequency. Fundamental means something like this. Just one segment. Okay. So here they are asking f5. f5 means 5 times the fundamental frequency. We found fundamental frequency. This one is 120. So we multiply it by 5 to get the fifth harmonic. Okay. Okay. So here are 2 more problems. Do it quickly as well, just like you did the previous ones. M over L, okay? M over L. And be careful with the units. They have given this in grams. You have to convert it to kilograms. So we can easily find the velocity, right? So let's first find the velocity and then go to the problem. Velocity is given by tension, which is 20, divided by mass density, m divided by L. They have directly given us that value, right? But it's in grams. We have to grams per meter. We have to convert it to kilograms per meter. So 1.5, 10 to the negative 3. So when you do this, you get the velocity as 115.47, 115.5 meters per second. Okay. So we have that. And now we can use V equals F lambda. V equals F lambda to find the lambda. So your lambda will be V divided by F dot. So when you have the correct frequency, you get the lambda for that frequency. So here they have given the fundamental resonance frequency, right? So the lambda value we will get will be for that fundamental frequency. So basically we are getting the lambda related to this one, this one node. Yes, we have to make this kilograms. Make sure, because we always have to substitute standard units. So when we do this, we get 115.47 to 20, and I got 0.5 5 to 4 meters. But this is lambda, right? They are not asking for lambda, they are asking for the length. So let's try to find the relationship between length and lambda. We know here half a lambda is equal to L, right? This length is half of a lambda. Therefore, L will be half of this value, 0.524 divided by 2, which is 0.26 meters. So your answer is A. So there were 3 steps, right? Find the velocity, find the lambda, and once you know the lambda, you can get L. So this M over L, you remember from last time, right? M over L is the linear mass density. So it is sometimes people refer to it as simple mu. Mu is M over L. Here they have directly given us the value of mu like this. That is the mass per meter, mass per unit length. Okay, so this one, a string of length 2.5 meters is fixed at both ends. So 2 ends should definitely have nodes. Okay. String vibrates at a frequency of 85. A standing wave with 5 loops formed. So 5 loops is 1. Oops. I don't think I can draw 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. And this whole length is 2.5 meters, right? Okay, let's go part by part. Part A, determine the distance between 2 adjacent nodes. So what is this distance? They're asking what is the length of one loop. You divide 2.5 by 5, right? There are 5 loops. So you divide 2.5 by 5, then you get 0.5. So that is the answer for part A. And part B, they ask what is the wavelength. So we know the wavelength is the length of 2 of these, right? That is one way because we already know length of one loop. We can just multiply it by 2. Or you can use the traditional way, like what we did before. You can use the whole thing. 5 lambda over 2 is equal to 2.5. Therefore, lambda is. So you can even do that. Okay. Still you get the answer. 1 meters. Part C. Determine the velocity of waves. So we know V is equal to F lambda. They have given the frequency which is 85 and we just found lambda. Lambda is 1. So your velocity is also 85 meters per second. And part D, determine the fundamental frequency of this string. So how can we determine the fundamental frequency? So there are few ways. One is we can divide this, right? So we know they have given F5 this, right? They have given this value because there are 5 of this here. They have given that as 85. Therefore, F naught is 85 over 5, which is 17. So that's the easy way. Or you can draw this and you can write the lambda. Lambda is 2 times L, right? Lambda is 2 times L. So this is the long method. Don't do this, but I will go through it also. So you can substitute in V equals F lambda. Frequency is given by V over lambda. We know velocity depends on the medium. It depends on the string. So it is still 85, but we found in part C. Lambda is 2 times L, so 5. 2 times 2.5, 70. Okay, so I got a request to go through part B again. Determine the wavelength. So if like in all previous, like when I did this part at the beginning, do you remember how we found the wavelength? So what is a wavelength? So wavelength is when you have two nodes, right? When you have two of these nodes, you not nodes, two of these loops, you have one wavelength. So here, how many loops you have? 1, 2, 3, 4, 5. Okay, you have 5 of these. 1, 2, 3, 4, 5. And also we know one of these stuff is half a lambda. So that's what I did here. So we have 5 of these. So 5 times we have 5 of half lambdas, and it is equal to 2.5. And that is how I got this. Or the other way is, easy method is this. We know 2 loops, like I said before, 2 loops makes 1 lambda. We already know the distance of one loop, right? In part A, we found it as 0.5. So 2 of that is 1. 1 is 0.5 and the other one is 0.5. So 2 of these makes 1. Okay. So this is a nice short answer problem. So they can give problems like this for short answers. Okay, so you're okay with this, right? So sound, you all know what sound is, right? Sound, you all know that it is a mechanical wave. We learned last time. Mechanical is something which needs a medium to travel. And also we know it is a longitudinal wave. So these are important. Why? For conceptual problems. Okay. And there are few characteristics of sound waves. So if we look at the speed of sound, the speed of the sound will vary with the medium. Usually, in solids, the speed is the highest. Okay. And speed of sound is lowest in gases. So you can see 3 examples here. So these are like not really needed, but like for conceptual problems, they can ask, right? Someone shouts and the sound goes through a metal piece and also through air, which will come first. Things like that. So here you can see steel, which is a solid, has a very high speed compared to air. Okay. Speed increases with the medium. Denser the medium, better. Okay. So the other characteristic of sound is the pitch. So pitch is something related to the frequency. We call something with a higher frequency high pitch. something with a lower frequency, low pitch. So we cannot, humans cannot hear all frequencies. You all know that, I think, more than me. So the audible range is from 20 to 20,000 hertz, and anything less than 20, lower limit, is called infrasonic, and anything beyond the upper limit is called the ultrasonic. Okay, those are just words. Okay, so the most important part is the loudness. Okay, so loudness is a sensation, or it's a sensation that we hear, that we feel, and it is related to the intensity. So higher the intensity, we hear a louder sound. But the important thing is that loudness, what we hear, is not really linearly correlated to the intensity. They are not linear. So we will learn how they are related later in the next slide. But the important thing is they are not linear. Okay. So I said it is related to the intensity. And to hear a sound, at least we need this much of intensity. So anything less than this value, we will not hear. And anything higher than this value will cause us pain. It will hurt our ears. So it is called the threshold of pain. And this value is called the threshold of hearing. So it's the minimum value that should be there for us to hear a sound. Okay. So like I said, this is the most important part. So like I said before, loudness is a sensation. It is something that we are going to feel. And also it is not linearly proportional to the intensity. So to measure the loudness, they have introduced some quantity called the sound level. Okay, sound level will give you what you hear, the loudness. Okay, so it is given by this equation beta. So this is beta, the sound level, and the unit sign decibel. Okay, deci is a unit similar to centi. You remember centi, milli, something like that. Deci is also some kind of a prefix. So we measure sound level using decibels, dB. And the equation has 10 times log. So check your calculator carefully. Log is not ln, okay? It is not ln. Okay, it is not the natural log. Here they are referring to the log to base 10. So here your base is not e, not like this. It is 10. So in your calculator, there should be something called log. So log the intensity divided by this constant. So this is the threshold of hearing. Okay. Threshold of pain was 1, right? 1 meters, 1 W meter squared. Okay, so when they ask you to find the sound level, you just have to plug it into this equation. This value right here is a constant, and this is the intensity that we are interested in. And this beta, when you calculate this, it will give you the sound level in decibels. And you can see from this equation that they are not linear, right? It is inside a log. Okay, so the other thing is, I'm not going to teach these log lowers, but these are very useful in solving problems. So we will see in problems, you might have to use them. So look at them, like you can refer them, right? Log A times B is equal to log A plus log B. So something like that. So we will do it when we go to those problems. And also you remember this equation from last time. Intensity is equal to power divided by the spherical radius, area. Okay. So I want you to try the first problem and tell me the answer as soon as possible. So I have given the necessary equations here. So you all know the steps, right? First find the intensity. Okay. And then use this equation to find the sound level. So they are asking about the level and the answers are in decibels. That means we have to use this equation. But to use that equation, we need the intensity. So let's first find the intensity. Intensity at 5 meters is equal to the power. Power is 10 to the 1 times 10 to the negative 3 because this is in milli, divided by 4 pi r squared, and r is 5 meters. So when you do this, you get 3.18 10 to the negative 6. So this is the intensity. Now that we know the intensity, we can use this equation. Beta 10 log intensity that we are interested in, 3.18 10 to the negative 6 divided by the threshold of hearing. Okay. And if you plug this whole thing to the calculator, you should get 65 decibel. Okay. So what is the answer you get for B? So some of you gave me the answers, not the second one. So what's the answer you get for the second one? If you have got it already, send it to me. So who got B and who got C? Is it B or C? So this question explains a very important concept. So they are saying the intensity level in decibels is 65 by one dog. So when you have two dogs, can you just write 65 plus 65 or 65 times 2 and write 130? Can you do that? No. The reason is we learned at the beginning that what we hear is not linearly proportional, right? So we can't do that. So what we need to do is we need to go through this equation again. So what's the current intensity? In new intensity is 2 times the old intensity. The reason is we have two dogs now. So initially our intensity was this, right? 3.18 from the previous question. It's the same question continuing. So this was our old intensity, that is for one dog. And when you have two dogs, you multiply this by 2. So we have the new intensity. Now we can plug it into this equation. Beta is given by 10 log I new is 3.18 10 to the negative 6 times 2 divided by I naught. So when you do this, you get 68 decibels. So can you see, although there were two dogs, the loudness you hear, it hasn't doubled. It has only increased by a little amount. 65 just became 68. So it is very important to know that you cannot multiply these decibel values they give. So tell me when once you are done. I want to go through the second question again with a different approach. So I have repeated the previous question again here. Assume that they did not give us the distance. So they just gave the question like this. Intensity level of one dog is this, 65. And what is the intensity level if there are two dogs? So we do not. So in this problem, we don't know the value of I. In the previous one, I used what we calculated before, right? So how can we do this? So let's first write what they are talking about. So what is this? What they are saying is 65, it's the beta, it is equal to 10 log intensity of one dog divided by I naught. So that is what they have given, right? So I is the intensity of one dog. So one way to do this problem is, you know I naught, right? I naught is a constant value. So you can solve for I. That is one method. So if you are going to solve for I, how do you do it? Do you know how to get rid of this log term? So I will kind of do it here, but it's not really necessary to do it. I'm going to show you a way how to avoid doing that. So 65 divided by 10, you get log I divided by I naught. So I just took this 10 to the other side. So how would you get rid of this log? Log is something to the base of 10. So look very carefully. This is math. So you put this whole thing, this 6.5, right, to the power of 10. So 10 to the power 6.5 is equal to I divided by I naught. That is how you get rid of a log. Okay. So when you take the anti-log, this is what you get. This part becomes the exponent of 10. Okay. So this is kind of a math part. So from this, you can get the value of I, right? I naught times 10 to the power 6.5. That is one way. So you can find I and then continue what we did before. So if you have I, you can do it. So now I'm going to do the other method, what they did in the lecture. So in the lecture, they used these logarithm laws, log laws. So we are going to do that here. So this is the equation for one dog. For two dogs, we know intensity is what? 2I, right? It should be 2 times this. So if I write the beta, it should be 10 log, and the intensity we are interested in is 2I, 2 dogs, divided by I naught. So what if I write this log term like this. 2 times I divided by I naught. So look at this very carefully. So can you apply this log law to this one, this term? So this is a multiplication, right? Log A times B can be written as log A plus log B. So we can consider this 2 as A and this part as B. So if I do that, I get 10 log 2. So that is my A plus log I divided by I naught. If I take off the bracket, I get 10 log 2, 10 log I divided by I naught. So what is this? 10 log I divided by I naught is this value, right? The decibel value for one dog, 65. And this 10 log 10, 10 log 2, you can directly put in the calculator. So even if you do this, you should get 68. So I wanted to go through this because this is the method that they used in the lecture. They directly write this in the lecture. So what they are really asking us is to find B2 minus B1, B final minus B initial. But before doing that, we have to know what is happening to the intensity. So let's say this is the initial intensity. Initial intensity is 4P, 4 pi r squared. And final intensity is P divided by, now they have doubled the distance. 4 pi 2r squared, right? So we can rewrite it as 4 pi r squared. And in the denominator, you have an extra 4. So this is same as our initial intensity. So final intensity is 1/4 of the initial intensity. Now we have these two things. Now we can start the problem. Now I'm going to write the equations. 10 log I final divided by I naught. That is the sound level when the distance is doubled. And the initial one is I initial divided by I naught. Okay, now to solve this, we definitely have to use these log rules. The reason is, although we know I initial and I final, we don't know the actual values, right? We can't just plug them and simplify. So what I'm going to do is I'm going to rewrite this in a nice way so that we can easily see what to do. So I'm going to take 10 out of the bracket and write the log terms closer to each other. So can you look at the equations and see that this is applicable, this log rule. So this is a subtraction, right? Log A minus log B can be written as a division. So if we consider this as A and this as B, we can divide these two quantities. So that is what I'm going to do. So I final divided by I naught, that is my A, and B, this is also fraction, that means I initial should go to the denominator and I naught should come to the numerator. So can you see that I naught get cancelled? Yes. And now we can substitute for I final. So what was I final? I final was 1/4 of I initial, right? So this is what I'm going to do. I initial divided by 4. And also in the denominator, I still have this I initial. So they get cancelled, right? I initial, I initial. So I get 10 log 1/4. So when you plug this in the calculator, you get a negative value, negative 6 decibels. That means it has dropped, right? The final decibel value is smaller than the initial. That is why you get a negative value. So your answer is C.